Fine. Yesterday I was mentioning about a Java applet, if you remember, which illustrates the graphical computation of the convolution operation in discrete time. I found it. This is not mine. It's from the Johns Hopkins University. So the web page you can see over there, pages.jh.edu/signals. If you go to signals, not to discrete time convolution, whatever, just forget about the rest, you will see a lot of signal processing applets there, which are all very beneficial, okay? Very useful applets. This is the discrete time convolution applet. At the left hand side you see some green dots, at the right hand side you see some blue dots. These two correspond to the two signals that should be convolved. One of them corresponds to the signal, the other one corresponds to the impulse response of the system in terms of the convolution. Soon today, right after this demonstration of the applet, I will show that they are interchangeable. I mean, it doesn't really matter which one is the impulse response and which one is the signal. You can just replace them. The convolution is the same. X convolution H is the same as H convolution X. We will see that. And over here, they replace or flip around not H but X. But it doesn't matter. It's the same because you can always interchange their places. Just a very nice demonstration. You can draw with your mouse, if you go to that page, some signals to the left and to the right, and then start sliding in the middle illustration, middle figure. The result will be shown as the third, as the fourth, the bottom figure over here. I will try to draw something here. Well, using the mouse it's not very accurate. I am trying to get a box shape as much as possible, okay, a flat surface, sort of. And then I will try to draw the same or the similar box shape here as well. What I want to show you is the result and how it behaves. Whenever I touch and start scrolling, you see this one is the flipped around version of the left hand side green figure. And I'm able to slide it using the mouse. Right? As you see, at the position of n is equal to -10, for example, we are here, n is equal to -9, -8, -7, -6. And just look at the yellowish figure at in the middle, this one. Okay? You see that there is no overlap, and the multiplication will give you 0 still over here. But after -5, they start overlapping, and you see that there is an impulse, which corresponds to the multiplication of the two impulse magnitudes that are overlapping over there. And then we will have two impulses overlapping, and then 3 impulses, and then 4, and then 5, and then 6 impulses, which is the maximum amount of overlap. They totally overlap here, because the sizes I have drawn for the two figures are the same. And then I slide further to the right. This time it becomes 5 overlaps, 4, 3, 2, and 1. And see what's going on at the bottom figure here. If there is 1 overlap, its summation is some value. If there are 2, the summation is a larger value. If there are 3, the summation is even a larger value. A larger, and at this point, with the complete overlap, it reaches to a peak. And then it becomes declining again. Look at the yellow circle at the bottom of the triangular shape at the bottom figure. Okay? That corresponds to the n point that I'm rendering. Now this thing that I tried is a very typical situation that happens when you try to convolve two rectangular shapes. The green at the top is a rectangular box. The blue at the right is a rectangular box. If you convolve two rectangles, they increase up to the maximum overlapping point and then they decrease. So there's an inclination and a declination. If the sizes of these two boxes are the same, it will identically produce a triangle. So the convolution of two equal size boxes is a triangle. Okay, keep in mind this one because the intuitive shapes may be important for you. I mean, it may save you some time. Now, I will make one of them. Let's make this one a little bit longer. Okay, a wider box, in other words. And then I will start scrolling. As you see, the figures are now erased. What kind of a figure do you expect at the bottom? Can any of you describe the convolution result? Exactly. It will enter and then enter more, enter more, enter more, so there's an inclination. But in the center, there is not a single peak point. It will go on. So there will be an inclination, a flat follow, and then after some points, it will start going out of the overlapping region, and then it will decline, going back to zero. Okay, look at that. Now it's starting to overlap more, and every additional overlap is contributing. We are at the third, fourth, fifth, and sixth. This stays the same for some time up to here. After that, it will start decreasing because the overlapping region, as you see, is becoming less and less. So this is the convolution result of two rectangular shapes if one of them is longer than the other one. And it doesn't matter which one is longer than the other one. Is there a way to... yeah, this erases everything. Now, let's fantasize on it. For example, let's make this one, again, some sort of a box shape. But let's make this one some negatives, a zero, and some positives, like this. It's gonna flip around the first one. But you could also do it by flipping around the second one, of course, whichever is appropriate for your visualization purposes. Now what will happen? Let's see. There's no overlap at -5, but at -4 there is a minus overlap, so the accumulation is negative. At -3 the accumulation is even more negative because two negative terms now contribute. Here nothing changes because there enters a zero, and then a positive one enters, which decreases, decreases the negative magnitude. That means an increase at the bottom figure, and then one more positive, which cancels, hopefully, everything, and go back to zero. And when you further go right, this time only the positive parts will start to incorporate here, a smaller positive contribution, and then no overlap. So this is a shape that first goes negative and then positive. But it may be different if this left-hand side pulse is shorter, like this and this. Only two pulses, for example. Then what's going to happen? Then the maximum overlap is here, a smaller overlap, then an overlap with a positive one, another positive one. So the shape that you get is becoming narrower. Let's make it even wider. Well, something like this. Okay. Then it's difficult not to overlap, of course, whenever you start arriving. you have this kind of a situation. Now, what does this effect mean? In the centers, ideally it's a zeros, a lot of zeros you will see in the bottom figure, in the middle. Because of the drawing imperfections, it's not completely zero. But what I'm trying to emphasize is that in the central places here, the positives and negatives are multiplying the same amount, so their summation contributes to zero. That's why at the bottom red line, red figure, you see some zeros in the central points. So there may be negatives, positives. There may these two may also have positives and negatives. Let's draw something like this. For example, both x and h are alternating. What kind of a thing will it be? The positive sides will collide with the negatives, which will produce something negative. Well, it's difficult, you see. It depends on how wide the right-hand side and left-hand side positive and negative parts. You just have to be very careful about this scrolling business to come up with some shape like this at the bottom. But this Java applet is quite beneficial for you. I'm just giving some examples about what you may expect. But you should try a lot of things. Just play with it. Okay? Try to draw some shapes. If these two were the shapes, then what would be the result? It may even be the case that I could make some screen captures from this Java applet. Okay. And then give you two candidates and one result as two candidates in the form of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 20 perhaps. And then I will give you 20 convolution results, and I will ask you which is which, 1A, 2C, 3B, okay? Just matching question could be asked. And in order for you to quickly solve so many convolution results, it may be a better idea that you play around with this thing. Okay. Now, I'm going to draw another thing. Let's draw a triangle here, which is h of n. Well, I'm unable to do that even. Something like this. And here, I put one impulse in the center. The question here is, what's the convolution result? Well, let's not talk about the scales. I'm not talking about scales, but it should be the same triangle, right? The reason for that, okay, sometimes people just forget the concept of convolution, where it comes from. It comes from the concept of impulse response, okay, isn't it? Now, isn't this an impulse at the left? And the right-hand side is the impulse response. So what will be the result? If the impulse comes, impulse response goes out. There is no need for the convolution. Convolution with an impulse produces the same thing. Of course, depending on where the impulse is. Well, okay, let's first see what happens. Still, this convolution makes an illustration. But as you see, the red figure, within a scale, of course, is the same as the blue one. The shape is the same. Now, what if I put the impulse here? Then what will be the response? Which is the convolution result. What's the convolution result? It would be the impulse of the system to this impulse. And the response will be delayed by an amount of 4, obviously, isn't it? It will be just a delayed version. The input impulse comes late, therefore the output triangular impulse response will also come late. Look at that. It's the same triangular shape, but it's only shifted towards right by the same amount of the shift imposed by the impulse. Okay, now let's see what happens here. what is the response? Or what is the convolution? These two are the same questions. We will have two separate triangles, right? One of them will be the delayed, the other one will be the lagged. Because the leftmost impulse will generate one triangular response, the rightmost one will also generate a separate triangular response, like this. Two separate convolutions. Now this also provides us with the linearity property utilization for the computation of convolution. If you can split your impulse response or your input, okay, one of those two signals or both of them, if you can split into some easier portions, it may be a very good idea to perform individual convolutions and then accumulate the results. Convolve with the right hand side, convolve with the left hand side, and add the result. It's here. It may be beneficial if, for example, the two impulses are a little bit near, like this. Because when you're sliding, the overlappings, this one will start overlapping, and afterwards this one will also start overlapping, and then later on this one will go out, this one will further go in. What's going on? It may be a difficult and cumbersome operation to graphically convolve. So forget about that. Think of these as two individual impulses, and each of them will have a triangular response. One of the triangles will be a little bit at the right hand side, the other one will be a little bit at the left hand side, right? Two triangles. What's the summation of two triangles? It will be something that climbs up, probably stays the same or something, and then goes down. The summation of two triangles. Let's see if that is really the case. Inclination, somehow a flat top, and then a declination. So that is something that I would recommend for thinking about. Another thing you could think about is, let's consider this rectangular shape again, and let's have a rectangle here at the same size and an impulse here. Okay, I put the impulse here. That's what I'm talking about, right? We know how it behaves if you convolve two equal sized rectangles. It will give you a triangle. So we know the result of the convolution of this portion and this portion. We know the convolution results. If you're solving it on a piece of paper in the exam, you should first convolve these two and draw the triangle. Okay, and then forget about that convolution. Next, convolve this impulse with this rectangular box, which would give the same box. So the result is the combination of that box in the center and the result, the previous result, which was a triangle, whatever that shape is. Let's see how it looks like. It looks like this, obviously. The rectangular box in the center is here, and then a triangle comes into the picture, and we see that some overlapping occurs here. If we try to eliminate this impulse and put it here, for example, a bit nearer, then it would be more meaningful, I guess. We have a triangle and a rectangle at the position of the new impulse, which is something like this. Now here, what you see is an inclination followed or added by some flat rectangular shape at this point. It may be a better idea for the scaling purposes to, sorry, not this one, to make this impulse taller and make these shorter, like this. then you will better understand what I'm talking about. This large impulse will produce a rectangle in the center which exhibits itself here. And then there is also an inclination. You have to sample by sample add those two individual separate convolution results. Okay, let's erase. Let's take a look at this situation. What's the convolution result? How will you compute this? You have to first convolve the leftmost green with the leftmost blue, and then convolve the leftmost green with the rightmost blue. Then rightmost green with the leftmost blue, and rightmost green with the rightmost blue. Just make cross convolutions like multiplication. Okay, and each of them will give you some triangles, hopefully, because they are all boxes with the same width of 4. I don't know how it all looks like. Okay, this is the situation. What does this mean? What do we see here? We have a triangle at the left, which is the convolution of the two leftmost figures, and then there's a convolution of the two rightmost figures at the right. The convolution of the left with the right will meet in the center. It will make a triangle. And the convolution of the right with the left will also meet in the center, which will also make a triangle in the center. And that's why you don't see 4 separate triangles. 2 of them are in the center, and when they are added, it just makes a taller, a bigger triangle. It's an addition of 2 separate impulses that you see in the center. Okay? Yeah. Well, that's, yeah, in the old graphical way of computation, that would mean, yeah, from -20 to +20, you have to compute one by one everything. But you shouldn't do that. You should only focus to this and this, for example, whose convolutions will give you this. And then draw it there. Finish. Only 8 computations. 4 from here, and with the sliding, 7 computations in fact. And then convolve this one with this one, and it will be in the center because one of them is shifted towards the left, the other one shifted towards right. Their shifting effects will cancel and meet in the center to form a triangular shape in the center. Draw it. You have to draw 4 separate triangles. 2 of them will meet in the center. You shouldn't do it from -20 to +20. It would be headache. Yeah.
Hocam zamanlamasını nasıl yapacağız? Yani sonucun zamanlamasını nasıl ayarlayacağız? 2 tane şey konulu ederken.
What I would recommend is something like this. Let's erase this. Let's also erase this one. I'm gonna draw a box here, and I'm gonna draw a box here. One of them seems to be shifted. I mean, the center of that shape is at the right hand side, or you can think of the starting points. Just look at the starting points of these 2 rectangular boxes. They will definitely make a triangle. We know that. But where does that triangle start from? You can either check it by flipping around and then sliding for checking the meeting point, which is a good idea. Or you can say that one of them is shifting towards left, and the other one is shifting towards right, and their overall effects should cancel in the center. First, you have to know the size of the output. What is the size of the output? Okay, that's another lecture that I would say quite soon, but it's maybe a better time to indicate that right now. What is the length of the triangle? Or what is the length of the output convolution results? If one of them is length 4 and the other one is length 4, they may be rectangles or other things, but you flip around one of them and then start overlapping, sliding and overlapping. How many overlapping shifts will there be? Yeah. In general, if one of the sizes is n and the other one is m, the convolution result is n plus m minus 1. Okay, so this is 4 plus 4 minus 1, 7. So there will be 7 items, and 7 is an odd number. And that odd number will produce the center, the peak of the triangle in the center, because they are balanced to the right and to the left. So intuitively I can say that this is a length 7 triangle, 3 items to the right, 3 items to the left, and 1 item in the center. 3 plus 3 plus 1 is 7. And let's quickly draw it and look at the below red figure. Yeah. This. It flips around x. So x, it was originally a negative shift in the time. By flipping around, it becomes positive in time. And at n is equal to 0, the flipped around version of x is identical to h. So they completely overlap at n is equal to 0. How about this one? Now, let's try to locate intuitively without seeing what's happening. The green figure is shifted towards right, towards left by an amount of 1, 2, 3, 4, 5, 6. Right? It is 6 shifted towards left, whereas the other one is 0 shifted, let's say, if the starting point is given as the 0 point. So their effects with respect to the previous case, how much different will it be? I mean, where will be the peak of the triangle? It will be at -3, because with respect to the previous case, it is 3 shifted towards left. If you're not very sure about your intuitions, I would recommend that you just try to flip around. Just flip around one of them and slide to see where, at which point of n, it performs a maximum overlap. And that will be the center of the triangle. And as you see, yeah, this is the point where it makes complete overlap, and that corresponds to n is equal to -3. So our triangle is now 3 shifted towards left. In order to compensate for that, I could draw something like this probably, right? And then the convolution of these two will be where? Where will be the peak of the triangle for the convolution of the two? Yeah. It will be at the center. Well, I guess that's why I recommend this applet, and you play around with it. Just make examples, make exercises, and see what sort of a shift does it correspond to. Always keep in your minds the positive and negative examples as well. For example, I'm trying to make some oscillations over there. Some ugly figures. That would be quite messy. But they do correspond to some maximum overlaps at some points if their periods are the same. I'm not sure whether I was able to draw the similar periods. But for example, somewhere like this, they very much overlap, and somewhere else they don't overlap. I am unable to draw it. If they provide some fixed, there's a selection of some fixed shapes, it would be a better idea. What I was trying to emphasize was something like this. If you have an oscillation cycle like this, a period, and the same, or the similar at least, sorry about that. In the center, they give, if they have the same positive and negative parts, like I have drawn at the top, in the center they should give you a 0 if the negative and positive oscillations make the same zero crossing at the same 0 point. And they make a peak. Well, they excuse me about that. They should make a peak at the 0 point in the negative sense. Let me at least try to draw some rectangular boxes because I'm having difficulties in sinusoidal drawings. Something like this. Now, at this point is the exact opposite of the previous. So the blue and the green are just the opposites of each other, and their multiplications will give you a lot of negative numbers. And those negative numbers, as you see at the red figure, will provide you with a peak, negative peak. I'm sorry, from here. So first negative, so first positive, because the same signs will match. Negative and negative with positive and positive at the right hand side and the left hand side, but in the centers, around the centers, the negatives will contribute more to provide you with a peak. In telecommunications, the detection of some pulses like this in continuous time basically, but the illustration is the same as the discrete time, requires the knowledge of the shape. Is the shape that is coming the same as this, for example? And the excellent method to detect the shape is to use the same shape flipped around version of the same shape for convolution. Let's draw the flipped around version of this. Nope, this is too much. Yeah. The green is hopefully the flipped around version of the blue. Now, when you convolve with it, they identically match in the center this time, and then they go away. What they do is they perform a convolution with the flipped around version of the expected pulse shape, and just take one sample from the 0 point. If that sample is big enough, above a threshold, for example, then we say that we have detected the pulse. So convolution is like making or performing a correlation, a cross correlation between two shapes. If two shapes are just mirror symmetries of each other, in the convolution they will give you a peak, a very large number. So convolutional filters are also used in telecommunications, therefore. We had an exponential decay example, if you remember, and at the right hand side we had a unit step. Well, it was just the opposite, but anyway, their replacements don't matter. It was something like this. A unit step and an exponential decay. You remember these? It was the question yesterday. And then when we convolve them, see what's happening. Well, you should only look up to this point because I am unable to draw a unit step function that goes indefinitely. Now this red figure is increasing with an asymptotic convergence to 1/1 minus alpha. Of course, after this point, since I'm not able to draw the unit step indefinitely, it makes a jump towards the 0. But look at the shape around here. Isn't it the shape that we have drawn yesterday? Okay. Well, these are the examples. If you go to this much, not discrete time conv or anything, up to signals portion, you will see a lot of Java applets. For example, the next Java applet is regarding the continuous time convolution, which is excellent. It's even more difficult to convolve in continuous time, as you may guess. You will see lots of Fourier related applets, etc. So keep in mind that web page, this web page. Okay? Pages, GHEDU/signals. I had a lot of difficulty in making this thing run, okay, in my tablet. It just didn't run. Java is having issues, okay. Java just seems not to work anymore with the web pages. Due to security settings, it says I'm unable to load it, I cannot run it, your system settings prohibit, etc. So I had to struggle. You may also do that. You may also struggle, but it's very rewarding. In the end, I had it run. Please run it. Okay, I will continue with the continuous time convolution. So it may be a better time to give a stop at this point, but 15 minutes later, please, let's meet again, okay? So let's stop.